Hello, this is Irie from Frasware.com, and today I'll be covering the FUnit editor extension for Unity. To start off, I'll briefly introduce you to what FUnit is and how you can use it. Once this short presentation is complete, we'll jump straight into the Unity editor and begin discussing the plugin and creating some different test cases. FUnit is an editor extension made for Unity. It's a unit testing framework of sorts that allows you to test the functionality of your code and scripts. Testing with FUnit is performed by using two different types of test frameworks, traditional unit tests and a special type called yielding tests. Let's examine both of these briefly. A traditional unit test is a piece of code, usually written in the form of a method that is called by a testing framework. The method consists of statements that manipulates one or more pieces of data in your code and asserts whether or not the data are correct. In Unity, unit tests are generally written for low-level or back-end code that's not attached to scripts. Writing unit tests with FUnit is very similar to writing unit tests that use other frameworks. If you've unit tested with other frameworks before, you'll have no trouble doing so with FUnit. One of the great things about FUnit, however, is its ability to run the tests you write directly within the editor itself. You won't have to use a third-party editor to see the results. So what's a yielding test? Yielding tests are what make FUnit rather unique. In FUnit, a yielding test is also a method that tests a unit of code using assertions like a unit test. The primary difference between this type of test and a traditional unit test, however, is that you actually can test code that you attach to your game object. Yield tests are specifically designed around the concept of time, and therefore, you can write tests for code that depends on time during its execution. Yield tests are heavily based on the coroutine system used in Unity's API, and, in fact, is where the name originates from. These tests are structured similarly to unit tests, but their syntax and testing strategies differ. Yield tests, like unit tests, can be run directly in the Unity editor, and the best part is you can actually watch your tests run in the scene. Now that we've seen a short overview of the extension, let's hop into the Unity editor and begin some examples. Alright, let's get started. To begin, you'll want to open up your Unity project. In my case, I've created a new empty project for the purpose of these examples. Once you have your project open, you want to go ahead and import FUnit. In my case, I've already got the file saved to my computer, so I'm going to browse for it and import it that way. You may also import it through the Asset Store window as well. Note all the files that are included in the package. When you import FUnit, you must include the editor and framework folders and all of their subfolders and files, as well as the FUnit environment prefab. These files are required for the plugin to run. The example folder is optional, and, in fact, you'll probably want to uncheck this folder when you import it into your own projects. It is useful, however, if you're just getting started and want to see a few examples of how to create tests and how they run in the editor. I'm going to go ahead and import the examples file included in the package since we're going to be testing some of the scripts provided, but I'm going to exclude the tests folder since we're going to be writing tests from scratch. Go ahead and import the package and wait for it to load. Now that it's loaded, let's go ahead and open it up. Under Window, FUnit, you'll find two options that allow you to open up two different FUnit windows. Let's open the first one. This is the main FUnit window. It is here all of your tests will be displayed and where you'll be able to execute them. Right now, no tests are present in the project, and so no tests have been loaded. Let's go ahead and dock this window since we'll use it later on. Finally, let's open up the FUnit console. The FUnit console is used by FUnit to log errors that occur during the execution of your tests. This is very useful for determining why a test failed and where it failed in the code. I'll go ahead and dock this window too. Now that we have the editor open and docked, let's create some tests. To begin, we will create a few unit tests. Before we can write these tests, however, we first need code to test. In this example, we will unit test one file that is included in the examples folder. The file in question is called inventory, and it is located in the scripts subfolder under the examples folder. Let's open this up and see what we'll be testing. The inventory class is a simple class that keeps track of items that are added to it. Think of this class as the logic that would keep track of a player's items in a game. I won't cover all the details that go into making this class what it is, but I do briefly want to mention the two methods it contains. The first method is add item. Add item, like its name suggests, takes an item and adds it to the inventory. Our inventory is fairly robust, however, and can hold items in different ways. If two or more of the same items added to the inventory are stackable, then they are added to the inventory while only counting towards one of the use slots of the total capacity of the inventory. However, each stack itself has a maximum capacity it can hold before it can no longer stack. It's at this point when our inventory would need to allocate another slot to store the new item. Also, since our inventory has limited space, we must ensure that we don't try to add items to it when it's full. This method addresses all these possibilities and will update the inventory accordingly. Finally, we have a method called getItem, which simply returns the item in the inventory at the specified slot index. What we want to do is test these methods and ensure that they work correctly as per our specifications. We will create a few unit tests to do this. To create unit tests, we must first create a class that will contain the test methods themselves. Before we do this, let's perform a couple steps that will help organize our tests. First, let's create a new folder called Tests. It doesn't matter where you create it, but I'll go ahead and create it in the example folder. This folder will hold and organize our tests so that they're easier to manage. Next, let's tell FUnit where to locate our tests. In the FUnit editor, click on Options. Note the field called Tests Directory. As you can see, it already points to the path where our tests are going to be stored. If you choose to store your tests somewhere else in your project, simply write the path to them in the field provided here. While this step is optional, providing FUnit with a directory for where you will store your tests will improve FUnit's performance when it gathers data about the types of tests you have written. Note that there are two more options here. If Find Tests After Compile is checked, FUnit will automatically scan your project for newly created or modified tests. If unchecked, however, you'll manually need to tell FUnit to scan for new tests by clicking on the button Find Tests that appears on the FUnit window when this option is disabled. Lastly, there's a Skin option which allows you to match FUnit's color scheme to that of your own Unity editor. Free or Pro. Now that we have everything set up, let's create a class that will test our inventory class. In the test subfolder, let's create a new C# script called inventory test. Now let's open it up and delete all the code that we won't need. The first thing that we need to do is make sure we include the FUnit namespace. Doing so will allow us to access the required classes and attributes needed to make our tests. Next, we need to set up the class so that FUnit recognizes it as a test container. This process involves two steps. The first is to make the class inherit from the class unit test, since we want to unit test our inventory class. The second step is to apply the FUnit test class attribute to our test class. Once we've done this, we can save it, go back to the Unity editor, and compile. You'll note that after the editor finished compiling our code, FUnit detected our new test class. There are no tests that we can run, however, since we've not created them yet. We will create them very shortly. Before we create our first unit test, we need to do some minor setup to our test class so that we can create our tests. Since we want to test the inventory class, let's go ahead and create a variable that will store a reference to an inventory object. Let's also create a variable that will hold our item database, which is a factory-like class that simply returns pre-built items. This class is also included in this package should you want to look at what it does, but for the purposes of these tests, the implementation isn't important. Now that we have the necessary variable set up, we need to create the objects and assign the references to them. But how do we do that? FUnit provides a special type of method referred to as a setup method. This type of method is called by the framework once before each and every test in the test class is called. Creating this type of method is very useful for setting up data that you will use during a test case. Let's create the setup method. To do so, create a new method that returns void. The name of the method does not matter, but by convention I'll call it setup. In this method, let's simply create our objects and set them up how we want to. As a default, I'm going to set our inventory capacity to 10. This way, at the beginning of each test, our inventory will begin with a capacity of 10. Now that we've written all the code that will initialize the data we need for our test, we must signify that this method should be used as a setup method during FUnit's execution of it. To do this, we simply tag the method with the FUnit setup attribute, and that's it. This method will now be called once before every test method in the class is executed. Alright, now we can actually write some tests. To begin, let's create a very simple test that adds a single item to the inventory and checks that it was added correctly. In FUnit, all test methods must be public, return void, and have no parameters. The name of the methods are up to you. So let's create a method of this signature called addItemTest. In the method body will be the code that defines our test. So the first thing we want to do is add an item to the inventory. Let's go ahead and do this by calling the addItem method on the inventory object we created during setup and passing it the second item in our item database, which happens to be an item called Bronze Battle Plate. Next, let's attempt to get this item from our inventory using its getItem method. Since we want to get the first item in our inventory, we'll pass an index of 0. And that's what we wanted to do in this test, add a single item to the inventory. But now comes the most important part of the test, the part where we actually check if the data are correct. Doing this is simple by utilizing the methods provided in the assert class. In this case, we want to assert two things, that our inventory size is now equal to 1, and that the item stored there is in fact the item we added earlier. For the first case, we'll use the assert_equal method of the assert class. Assert_equal takes two parameters of the same type, where the first parameter represents an actual value and the second parameter represents an expected value. Well, we expect our inventory is of size 1, so we'll use that value as a second parameter. For the first parameter, or the actual value, we'll use the inventory class's slotsUsed property to get the current size of the inventory. Once this line is executed during the test, these two values will be compared. If they match, the test will continue. If they don't, the test will fail here and go on to the next test if there is one. For the second case, or checking whether the item stored is the actual item we added, we'll also use another assert_equal statement. This time we're going to compare the name of the item that we stored in the inventory to the name of the item we expect to be stored in the inventory. To do this, we'll pass the name of the item to the first parameter of assert_equal using the item's name property, and then we'll pass a string matching the name of the item we expect to see. And that's it. We've written our first unit test for FUnit. Now let's save the file and go back into the editor so it can compile. You'll notice that FUnit hasn't located our test. The reason for this is because we haven't signified to FUnit that the method we wrote is actually a test. To do this, let's simply go back to the test that we wrote and add to it the attribute called FUnit Test. Doing so will let FUnit know that this method should be treated as a test. Methods that appear in your test class that aren't tagged with this attribute will not be treated as a test and, as such, will not show up as one in the FUnit window. Therefore, you are free to create any methods that you like in your test class that can help facilitate writing tests, such as helper methods. Let's save again and go back into the editor. Now you'll notice that the test is indeed showing up in the FUnit window. Notice the little white icon with the question mark in it to the left of the class name. This icon indicates that the test class contains tests that haven't been executed yet. Before we run this test, we must do one more thing. Simply drag and drop the FUnit environment prefab found in the root folder of the FUnit package into the current scene. This object must be somewhere at the root of your scene hierarchy to run any type of test. If it's not present, you'll be notified with an error should you try to run FUnit without its presence. Now we can run the test that we just wrote. To do so, let's click on the Run All Tests button under the Unit Test section. Notice how the Unity editor started playing and the test was executed. Notice how our test passed, as indicated by the green bar at the top of the window. You can also see that the test name has a green check mark beside it, indicating it passed the last time it was executed. A green check mark beside our test class indicates all of its methods have also passed. Note that there are several ways to run tests in the FUnit window. One way is to execute them all, like we just did. Another way is to run tests that are checked only, or by running tests in a single test class. To run a single test case, you can right-click on the test and click Test. Let's go back into our test class and create one more test, a test that will determine if stackable items are added to the inventory correctly. The next test we'll create is one that adds a stackable item to the inventory 3 times and checks that the item stacks correctly while only taking up a single slot in our inventory. First, we must create the method body, similar to the way we did previously, but this time tagging it with the FUnit Test attribute. Now we'll add 3 items to the inventory. In this example, we'll add 3 invisibility potions, which are stackable items. After adding the items, we'll again get a reference to the first item that is stored in our inventory so we can use it in our assertions. Since the items we added were the same and they were stackable, we should expect our inventory to have only used up one slot. We'll test this with an assert equal statement. We also want to make sure that the item is stacked properly. The item class has a stack count property, which simply returns the number of items in its stack. Using another assert equal statement, we can test that the stack count is in fact 3. As a side note, we could also use the assert true method of the assert class to test the same thing. Simply supply a condition we expect to be true, or that stack count is equal to 3. Now that we've written the test, let's again save and go back into the Unity editor. Notice that our new test is showing up and that it hasn't been executed yet. Let's execute our new test by right-clicking on it and clicking Test. Notice that the test also passes, and so far our inventory class is behaving like we expect it to. Let's quickly go back to the test and make a small change. Instead of adding 3 invisibility potions, which are stackable, let's add 3 bronze battle plates, or the item we worked with in the last example, which are not stackable. Save the file and go back to the editor. Let's run the test again to see if it passes. As you can see, the test fails, and this is to be expected because of the way our inventory class stores items. Note that in the FUnit console, we are notified of an insertion exception, and we're given a little bit of detail as to why the test failed. It says that the number it expected was 1, but the actual value was 3. This is because we added 3 of the same item that wasn't stackable, and thus 3 slots are taken in the inventory instead of 1. The line number of the error is also shown, and we can verify that this line in our test is where the test failed. And that's the basics of unit testing with FUnit for Unity. We're now ready to begin yield testing. Remember before I mentioned that with yield testing you can write tests for mono-behavior derived classes or scripts that you attach to game objects. Testing classes such as these, however, presents a bit of a challenge because you generally have things like time that affect the script's behavior. In unit tests, you execute a single line of code one after the other as a single uninterruptible block. In cases where the execution of your code depends on time, for example where you have to wait an arbitrary number of seconds for an action to occur, unit testing will be insufficient. Yield testing, however, is designed so that you can pause its execution and wait for certain conditions to occur before continuing a test. Using this type of strategy opens up a near infinite amount of possible test cases you could design to test your scripts. To see what I mean, and to learn the basics of yield testing with FUnit, we'll go over a simple example. First, like we did earlier, let's briefly discuss the classes we're going to test. For this example, we're going to test the NPC controller script that is included in the FUnit package. The script allows us to control the movement of the game object it's attached to. Its functionality is heavily dependent on another script, Waypoint Controller. In the NPC controller class, there are 2 methods of interest to us, and ones we want to test. The first one is move, which takes a vector 3 as its argument. This method simply moves the game object to the location specified by the provided vector. The second method is also called move, but it takes a list of waypoint objects as its arguments. When executed, this method will move the NPC to the desired location specified by the waypoint, or 3D points in space, one after the other. Finally, there is one part of the waypoint controller class that will be of interest to us for our test. This is the waypoint completed event. As the name implies, this event is fired each time the game object has reached one of the specified waypoints in its movement. Creating an event handler and listening for this event will be helpful when we write our tests in a few moments. Now that we know what we're testing, let's go ahead and create a new test class. Back in the Unity editor, let's create a new test class in the test folder we created earlier and call it NPC Controller Test. As before, open the new file, delete the code that we don't need, and include the FUnit namespace. In our unit test example, we changed our test class to inherit from the unit test class. In this case, we'll want to inherit from the yielding test class instead. We'll also want to tag our class with the FUnit test class attribute so that we can run our tests later, just like we did for unit tests. Unlike unit tests, however, yielding tests generally involve interacting with a scene, or the game that runs when you press the play button in the Unity editor. We'll want to set up the scene in a minimalistic way, or a way where only objects we care about are in the scene. We do this so we can minimize the influence that other game objects may have on the objects we want to test in our scene. Like with unit tests, we can set up our testing environment once before each test is run. But before I cover the setup method, I'm going to first create a few variables that we will need later on. Don't worry about what these are for just yet. We'll discuss their purpose as we need them. Now let's go ahead and create the setup method. Since this is a yield test, the process for creating a setup method is a little different than when you create one for a unit test. In particular, the method signature is different. Instead of returning void, we must return a reference to an IEnumerator object. If you've worked with coroutines before in Unity, you'll already be familiar with this object. If you haven't, I recommend checking out the link provided in the description below that covers the coroutine system in Unity. Other than the return type, the setup method for yield testing is the same as for a unit test. It must be public, have no arguments, and be tagged with the FUnit setup attribute. Now we can set up our scene and our test class so that we'll be ready for each test. The first thing we're going to do is load the scene that we'll be testing in, and we will do so using the application.loadLevel method provided in the Unity API. This step is extremely important because we want to reset our scene for each test, or start fresh. We don't want game objects in the scene to remain and interfere with the next tests. Before we continue, let's examine the scene we'll be loading for this test. The scene is very simple. All that's visible is a green plane which we use for our character to walk on. Note the FUnit environment prefab object in the scene hierarchy. Remember, this object must be present in each scene we wish to run tests in. Finally, if you plan to load a scene in one of your tests, like we'll be doing in this example, remember to first add the scene to Unity's Scenes and Build list under the Build settings if it's not already there. The next thing we want to do is also very important. We want to tell FUnit that we want to wait until the next frame before processing the rest of our setup method. Why is this important? Because we want to allow Unity enough time to initialize a scene for us before we start attempting to manipulate it. To do this, create a yield statement, or a statement that basically says, sit here until this condition occurs. In this case, we'll simply return null since we just want to wait for one frame. It's important to note that the setup method must include some form of a yield statement, even if you don't plan to load a scene each time it's called. Just simply put a yield return null statement at the end of your method and you'll be good to go. After this point in the code, the scene will be loaded and ready for us to interact with. Let's go ahead and create a game object that's already been defined for us in a prefab and store its reference. Let's also cache references to the game object's scripts we'll want to use later, as well as the game object's current transform. Finally, let's create and store a couple of event handlers. The first event handler we'll create is one that will handle the waypoint completed event that we discussed earlier. We're going to create this using a delegate so that we can store a reference to it for later use. For the method body of the code that executes when a waypoint has been reached, we're simply going to set a flag, finished moving, to true or false. We'll set it to true if there are no more waypoints left in the NPC's movement, or false if there are points still left untraveled. The last handler we'll want to create is a condition handler, or a handler that ultimately returns true or false when called. While the purpose of this handler isn't apparent yet, we'll shortly see how we can use it to control the flow of our tests. Now that the handlers have been created, we need to tell our waypoint controller about the handler we created a moment ago so that it's properly triggered. And that's it for the setup method. This should be enough to get us started with a few different tests. For our first test, let's simply move our NPC one time in one direction without using waypoints. To get started, we must create a method that FUnit will recognize as a yielding test. The structure to such a method is identical to the setup method we just created, with the difference that we'll want to tag this one with the FUnit test attribute instead of the FUnit setup attribute. For this test, we'll call it simple movement. Now we can begin writing the test. To move the NPC without waypoints, we'll use the NPC controller script's move method that takes a single vector3 as its argument. Let's go ahead and create a vector containing position of where we want to move the NPC. Say the position 10 units in front of where it was loaded, or the positive z direction. Next, we'll call the move method and give it the vector we just created. Finally, let's add an assert statement that checks if the NPC's current position is equal to that of the vector describing the position it should be in. Because this method returns an IEnumerator object, we need some form of yield statement. So, for now, let's just return null. Let's save the file and let it compile. You'll notice now that our new test class and its method is showing up under the yielding test section of the FUnit window. Let's go ahead and run the test that we just created. Notice that a couple of interesting things have happened. The first is that our scene loaded and our NPC moved forward. What you saw was the test actually executing in your scene. The second thing is that the test failed, even though the NPC does appear to be in the correct position when we examine its transform component in the inspector. The reason for this is simple, and to explain, let's go back and examine the test. When we added the assert statement before, we added it directly after the call to move on the NPC controller. Therefore, this statement is executed in the same frame that the call to move is executed. Therefore, our NPC hasn't actually moved at all. This is where time plays a significant role in our ability to test scripts, because the time between these two statements are practically zero, at least from the perspective of frames in Unity. We can't actually test that the NPC is in the correct position. At least under the unit testing principles, we couldn't. Because yield testing revolves around Unity's coroutine system, we can actually control when statements in our test are executed, and that's exactly what we'll do so that we can properly test the conditions we've set out to test. Let's add two new statements between the move call and the assertion. The first one we'll add is a yield statement, and we'll return a new coroutine here that we'll get from the coroutine EX library, or the extended coroutine library that is provided with FUnit. The coroutine that we're going to start is called timeout. The coroutine itself is fairly simple. It sits and waits, or yields, until the supplied condition becomes true or the amount of seconds provided has expired. For the condition, we'll supply the delegate we created earlier that simply returns true if the NPC has finished moving, or false if it hasn't. Notice that we set the finished moving flag in our event handler that is called on a waypoint completion event. All this condition delegate is doing is returning the current value of this flag. Finally, we'll provide a timeout of 10 or 10 seconds. This way, if, for whatever reason, our finished moving flag isn't set to true, the coroutine will expire, and it won't just sit there and hang. Lastly, we'll make a call to the check coroutine exception method. All this method does is check if errors occurred during a coroutine that was started from the extended library. It is important to note that it is necessary to make this call after you start such a coroutine. Otherwise, errors won't properly be reported by FUnit, and it'll appear that your tests passed when in fact they failed. Say, for example, the coroutine timed out before the condition you expected to be true occurred. What we've basically done here is say, sit here until the NPC has finished moving or until 10 seconds have passed. At that point, continue on with the test. In other words, we've basically controlled the flow of our test and allowed time to pass so that the objects in our scene could react. Using this technique, you can write some really powerful tests that could test a variety of different situations. Now we can save the file and go back into the editor. Now let's run the test. As you can see, the test has now passed just as we expected it to. For demonstration purposes, let's go back into the code and make a small change to the timeout coroutine. Instead of timing out at 10 seconds, let's change it to a timeout after 1 second. Now when we run it, you'll notice the test fails. This has occurred because the condition we supplied to the timeout coroutine didn't become true during its 1 second execution, or because our NPC hadn't finished moving during that 1 second. Let's write one more test, but this time let's make the NPC's movement more complex. We'll start off by creating a new test method called multiple movement. For this test, let's attempt to move the NPC in a square-like pattern, so that once it's finished moving, it's back where it started. To do this, we'll need 4 different waypoints, 1 point for each corner of the square. We'll also want to store them in a list so that we can use them later in the move method. I'll go ahead and create this list now. Now that we've defined the pattern of movement, let's tell our NPC controller to move to those places by calling the move method with our waypoint list. Like in the previous test, we'll want to yield until the NPC has finished moving or until a certain time has expired, in the event that something is wrong in our code and it never stops moving, for example. Also remember to check if any errors happen during the pause with the check coroutine exception call. Finally, we'll assert that the NPC's final position is that of where it started. Okay, now let's save it and go back to the editor so we can run the test. As you can see, the NPC is walking in the desired pattern and it stops right where we intended for it to stop, and the test passes. Let's go ahead and run both tests that we just created so we can see how tests are run in succession. Note that when one test finishes, the scene is reloaded and the new test is executed. This is how we designed our tests via the setup method. Designing a test class in such a way allows you to run multiple tests in a row without having to worry about tests running together. And that's it. We've just seen how we can use FUnit to test both code that we do attach to game objects and code that we do not. Now you should be able to adapt these techniques shown here to your own specifications so you can write tests for your own projects. Testing is an important part of software development, and FUnit allows you to easily and flexibly do so. It also allows you to test code that you may previously have thought you couldn't test. For full documentation and more examples, please visit our website provided in the description. If you have any questions, feel free to use FUnit's forum, also linked in the description, or comment below the video. Thanks for watching.